Now let me present an example of using the Abaqus-SwiftComp GUI to conduct the multiscale analysis. The example is an interlock woven composite plate. The whole structure is quite complicated. However, the plate is composed of repetitive cells in the in-plane directions, and the thickness is much smaller than the dimensions in the two other directions. Therefore, we can simplify the problem as a plate with the right plate stiffness matrix obtained from the SG homogenization analysis. In this example, the SG is 3D. This table shows the material properties in the SG. Because the structure of the SG is quite complicated, I have already created in the Abaqus. If you want to create it from the beginning for the 3D SG, it is just the same as what we usually do in Abaqus. First, we need to create the part geometry, and then we need to create materials, sections, and assign sections to the geometry. And also, we need to create mesh. There are several points that we need to pay attention to when creating mesh. First, the mesh should be created on the part, not on instance. Second, since SG analyses are conducted by SwiftComp, we only read the element connectivity and node coordinates from Abaqus to SwiftComp. In SwiftComp, there is no special element type like modified element type or integration reduced element type. Although we can assign element types like reduced integration element types like C3D20R in Abaqus, it will result in the same results as that obtained from using C3D20. We have already finished the preparation of the 3D SG. Let's go to the homogenization. Click the homogenization button and choose the model and part. And then we can choose to specify the SwiftComp file name or not. And we can also give the volume of the SG, but since it is a cube, we can keep it as default. And in the macro model dimension, we choose 2D shell. And the initial twist and curvature should be 0 because the shell is flat. And here we choose elastic to be the analysis type, and the element type and element orientation keep default. Click OK. Now we have obtained the effective ABD matrix of the interlock woven composite plate. We can import it into Abaqus and to conduct a macro shell FE analysis. Use this button and choose the SG name. Now we can find a new model named as the SG name is created, and the ABD matrix is imported into a general shell stiffness section in this model. In this model, we can also create the shell model and assign the created section to the geometry of the shell, and create a step, mesh, apply load, and carry out the analysis just as we usually do in Abaqus. Since this procedure takes time, I have already finished it. Now let's check the results. If we have special interest in the local fields, such as stress, strain at some locations, which is not close to the boundary of the plate, we can conduct a dehomogenization analysis using the sectional strain and curvatures from the shell analysis as the inputs. For example, if we have special interest at this point, we can extract the SE-SK, which are sectional strain and curvatures in Abaqus. Once we have these values, we can click the dehomogenization button, input these values, and click OK. If we also have interest in the local displacements, the macro displacement and the rotations at the point of the interest at the plate model should also be filled in. For the meaning of the inputs and outputs, please check the sctheory.pdf, which can be downloaded from CDM Hub, as I showed in the last video, Introduction and Installation of Abaqus-SwiftComp GUI. Now we have finished the dehomogenization analysis and can view local fields, such as the stress at nodes, strain at loads, and the displacement at nodes. We can still use the functions of Abaqus to analyze the results. For example, we can plot the stress at some specific paths. At path A, the stress looks like this. Conduct a multiscale analysis using mechanics of a structured genome could be very efficient and accurate. Compare the results obtained from the multiscale analysis and the 3D detailed FEA results. It was found that the maximum deflection of the shell analysis has only 1.6% of a difference compared with the 3D results. And we also compared the stress distribution at some specific paths. It was also found that the stress distribution is also very accurate compared with the 3D FEA results. Thank you. This is the end of the video. If you have any questions regarding to it, please go to the CDM Hub and post your questions on it. Thank you. See you next time.